So now I want to look at the case where we do have friction and we do have the hand force right there. And the work due to friction is a non-conservative friction. That doesn't mean it's a liberal force, right? It just means non-conservative right here, okay. And this one depends on the path right here. So it depends how you get from point A to point B. So let's look at a case right here. Suppose we have a block here. It's moving at some initial velocity, and at some later time it's going at a final velocity. And there's friction going in this direction. And we say, what's the work due to friction? Well, the work due to friction is the friction dot S, which is, S is that way, friction is this way. So it's the magnitude of this, magnitude of that, times the cosine of 180, which is -1. This distance is d, so it's just minus frictional force d. Since this work is a negative, energy is exiting the system. It's leaving the system. So now my energy equation is, remember what we had before was we had the sum of these three at the beginning equaled the sum of these three at the end. But now what we have is we have the initial energy minus how much we lost equals the final energy. So in this case right here, well, if I call this height 0, it has no gravitational, there's no spring in this problem. All we have is an initial kinetic minus how much we lost due to friction right here. That was the work due to friction. There's a negative right there. And over here, all we had was the final kinetic right here. So there's how we add the friction in there. We just look at the energy minus how much we lost due to all of our friction distances, if there were multiple ones, and that equals the final. Okay, so then we can go ahead and we can put in what the friction is. It's mu kn, and we know n is mg. So this is mu kmg. The m's drop out. Multiply by 2. The 2's drop out here and give you a 2 there. And then just take the square root of both sides. So there would be the final velocity. It should be less than the initial because you had friction slowing you down. Well, let's say we have work due to the hand and a friction. Let's say you're going to push on this thing with your hand with a nice constant push right here. Now, your hand force is also a non-conservative, and it depends on the path. Now, first of all, we already calculated what the work due to friction is. It's the same as this one over here. It was minus the friction times the distance. And the friction was mu kn, and n was mg. But now we also have the work due to the hand force right here, which is p dot s. And so it would be p dotted with the distance. Well, the angle between them is 0 degrees. And so it would just be p times d. Now, if we were to push in this direction while it was moving that way, then we would have had a minus right here. We would have been taking energy away from the system. But since this work due to P is a positive, we're adding it to the system. This one's taking it away, this one's adding it. So now, when we go and we write our energy equation, we have our initial energy minus our work due to friction, added what we added to it, and that equals the final energy. So this was really what my energy equation is going to look like. It's going to be whatever you had at the beginning, minus whatever you lost when you went from A to B, plus whatever you gained, or this could be negative, you could lose it, and that equals the final energy. So again, this term and this term were 0. We started out with kinetic. We lost, there's all of our friction. There's how much we added to it, and there's our final energy right here. If these two would have just been equal to each other and summed up to be 0, they two would have counteracted, and the work due to P would have just counteracted the work that you gained and the work you added with the one you lost right here. But here, so the final speed is your initial speed minus how much you lost plus kind of how much you gained right here. So that's how you handle that. So let's come down here and look at a case where we have not on a flat ground. Here we have an inclined plane. There's friction. You got a mu k. I should tell you, mu s, you never have work due to friction with mu s because this distance we have up here is the distance you slide. In mu s, you never slide right here. It's a static case. So work due to friction is only there for the kinetic case. So let's say we have a block. It starts from rest right here. You let it go. We push on it. We'll actually push on it with a constant force P. We've got friction. And when we get right to the spring right there, right at point B, we'll remove the force. We won't push on it anymore. So then it's just going to keep sliding right there because it has this velocity there. It hits a spring, compresses some maximum distance, so your velocity goes to 0. Okay, then it'd probably come back, but we're only going to stop it from we're not care what happens after that time. Okay, now, and I'm going to call the lowest spot h equals 0. Then this height, well, since this distance is s, the vertical height would be s sine theta. Remember, potential energy is just the vertical height. This distance is s plus d, so this is s plus d sine theta right here. So now, if we wanted to write out our energy equation between 2 points, any 2 points, let's just go from A to B. Okay, at A, right here, at A, right up there, we have potential energy, which is mg times this height, mg d plus s sine theta. That's where I got that. We have no spring energy there. The spring isn't stretched or compressed. We start from rest, so that's 0. Okay, and now when we go from A to B, we're going to lose work due to friction, minus friction times the distance you slid, right there. Plus, we helped it along. We gave it energy by P times D. So there is the energy we had at the beginning, minus what we lost when we went from here to plus what we gained. And these should be the energy at this point. At this point, you have potential, mg, s sine theta. You're also moving, so you also have kinetic. You have no spring because we just touched this. We haven't compressed it yet. So there's my energy equation between A and B. If we wanted to look at the energy equation, say, between A and C, we can go from here to here in one step too. At A, it's still the same. It's still, there's mg d plus s sine theta. But now the work due to friction, now we've lost friction all the way down to here. That would be minus friction times d plus s. Plus how much we helped it. Well, we helped it pd. And then we took our hand away, so there wasn't no help from here to here. So it's just from here to here. And then when we get down to here, we have no gravitational. H is 0. We have no kinetic. V is 0. All we have is spring energy right there. So there would be the energy equation between A and C. Now we could have gone just from B to C. We could pick any 2 points. At this point, we just have mgh. We have a velocity there, mg, 1/2 mv b squared. Now, when we go from here to here, we're only sliding a distance s, so it's minus friction times s. We didn't have a p force from here to here, so we don't have to worry about that term. And then by the time you get there, it's all spring energy. So there is the energy equation between B and C. And just to let you know, the frictional force for all of these, remember, is mu kn. But remember, n is this way. Mg, n is equal to mg cosine theta. So just from our forces. So frictional force is mu k mg cosine theta. That's what you'd use for the friction on all these. Okay, so that's how you handle this. So this is kind of the problem that you could, this kind of covers everything right here. You just look at all the sum of those 3 terms. And if you have multiple frictions, you'd have multiple frictional forces times distances. If you had multiple hands all pushing in there, you'd have multiple terms there. And that should equal the total final of all the terms right there. And so this is one equation that we can use to solve every single one of the problems, most of them in chapter 6 and 7. Okay.